Hello everyone and welcome back. My name is Mr. Cobalt, and in this video we're going to go over how to solve a problem that's asking you to give the, concentrations of all the species under certain conditions to start with. So let's get into this. Okay, so in this problem we're told at 35 degrees Celsius the Kc is equal to 1.6 times 10 to the negative 5 for the reaction, and then they give you the reaction. It's 2 NOCl gas in equilibrium with 2 NO gas and plus Cl2 gas. And they wanted us to calculate the concentrations of all the species at equilibrium for each of the following original mixtures. So what are the original mixtures? The original mixtures are for A, you have 1 mole of NOCl in a 1.0 liter container. B, you have 1 mole of NO and 0.50 moles of Cl2 in a 1.0 liter container. And then C, you have 1.00 moles of NO and 0.75 moles of Cl2 in a 1.0 liter container. Now, the first thing I want to point out is right away, they're giving you moles, but they're telling you it's in 1 liter, and we know that molarity is liters per mole. So here we can use the moles just as if we are using molarity, since 1 mole divided by a liter gives you 1 molar solution, or 1 molar concentration. Okay, so let's start with A. They're giving us to start with 1.0 moles in 1 liter, so that's 1 molar of the NOCl, and that's what we're starting with. And so what we need to do is find the species at the equilibrium, which means we're going to need to do an ice table. So let's go ahead and start that. So we're going to have an ice table. Here I have my equation. I'm going to have ICE. Okay, so the initial amount that I have that I'm starting with is 1 molar. So 1.0 moles in 1.0 liters is 1 molar. So we're going to have 1.0 molar to start with here. But then we don't have anything here. They didn't give us any information, so the assumption is we don't have anything there to start with. So we're going to have a 0 amount here and here. And then that tells us that it's going to shift in this direction because it's at equilibrium. There's going to be some species here and here. We have 0 here, so it's got to fill in that gap. So it's got to shift in this direction to make product. So we're going to lose a 2x amount here because we're following the stoichiometric ratios. Right, so we have the coefficient 2, 2, and 1. So we're going to lose a 2x here, and we're going to gain a 2x amount there, and we're going to gain an x amount there. So we add these together, and it becomes 1.0 minus 2x for the equilibrium concentration, and here we're going to have 2x for the equilibrium concentration, and we're just going to have x. So now we have the equilibrium concentrations of each of our species in terms of x. So, and they also gave us the Kc value, so we can solve for x. So let's write the Kc expression, the equilibrium constant expression for this equation. So it's products over reactants, so the concentration of the products raised to their stoichiometric amounts, the coefficients, over the concentration of the reactants raised to its stoichiometric amount, the coefficient. So here we're going to have the concentration of NO multiplied by, and that's raised to the 2nd power. Since we have a 2 coefficient there, this is a 2 power of 2, and then multiplied by Cl2 concentration raised to the power of 1. We don't write the ones, but it's 2 power of 1. over the concentration of NOCl. So we're going to have NOCl, and that's also raised to the power of 2 because it has a 2 coefficient. So now we have our expression for the equilibrium constant K, and so now we just plug in the equilibrium concentrations in terms of X. So this is going to be equal to, let's write down, 1.6 times 10 to the negative 5 is going to be equal to, so we have concentration of NO, so that's going to be 2x. So we're going to put 2x here, and it's squared. And then we're going to multiply the concentration of Cl2, which is x. So we're going to put that there. And then on the bottom we have the concentration of NOCl squared. So 1.0 minus 2x squared. So we're going to have 1.0 minus 2x, all of it squared. And now we can use the x is small approximation, because if you look at the original concentrations, right, we have 1.0 molar here, and we have 0 here. So this concentration compared to the Kc, notice the Kc is very, very small, right? So this is like a factor, 1 times 0 times 10 to the 0 power. So, so if you compare that to 10 to the negative 5, that's about a 100,000-fold difference. So that means that x is going to be really small. So therefore, we can assume that the x is negligible, and we can get rid of it in the equation. So here, since we're subtracting 2x, we're going to say, well, subtracting such a small amount, if x is so small, it's not really going to affect the initial concentration. So the final concentration is going to be equal to the initial concentration. So then we can get rid of the 2x here. So we're going to have 2x squared times x over 1 squared. Now we can start to solve this. So this is going to be equal to, well, 2x squared is going to be 4x. 4x then multiplied by x is going to give us 4x squared. And then, of course, 1 squared is 1 divided by 1 is just going to give us 4x. So, right, it's just going to be 4x squared over 1. And that's going to be equal to 1.6 times 10 to the negative 5. We don't need the 1 here, so we can rewrite this as 4x. Oops, I meant 4x cubed, right? So because this is 2x squared, or 2x, all of it squared is going to be 4x squared, and then multiplied by x is going to be 4x cubed. Sorry about that. Okay, so now that I fixed my mistake, so now we can solve for x. So we divide both sides by 4. So that's going to give us 4.0 times 10 to the negative 6 is equal to x cubed. So then all we need to do is take the cube root of both sides, and then we get x is equal to 0.01587. 0.01587. So there's our x value. Okay? And so now we can go ahead and plug that into here for the concentration of our species at equilibrium. Now, the one thing I want to point out is we could possibly put x in here and subtract from 1.0, but that would contradict what we had said before. We said before that because the Kc value is so much smaller than the initial concentration, that subtracting the 2x here would be negligible, such that the initial concentration would be the same as the equilibrium concentration. So therefore, according to our assumption then, the concentration of NaCl at equilibrium should be the same as the concentration that we initially started with. So that should be 1.0 molar. Now for the concentration of these, we can just plug in X and calculate. So here, the concentration of NO at equilibrium is going to be equal to 2X, which of course if we plug in X is going to be 2 times this number, 0.01587. And then if we calculate that, we get 0.3172, 0.3172, and if we round to 2 sig figs, because we originally started with 2 sig figs, that's going to be rounded to 0.32 molar. And then we can do the same thing for Cl2. So let me get rid of this to give me some self-room. Okay. And so now we are going to calculate that for this one. But we don't really need to do any calculation because it's X, and X is 0.1586. So the concentration of Cl2 is going to be equal to X, which is 0.01587. If we round that to 2 sig figs, X, or I should say, this concentration for Cl2 is equal to 0.016 molar. So now we have the concentrations of each of the species under these original starting concentrations. Okay, so what about B? Let's go ahead and do B. So I'm going to have to erase let's start over. Okay, so in this case here, we're starting with 1.00 moles of NO and 0.50 moles of Cl2 in a 1.0 liter container. So again, since we're in a 1 liter container, then we can treat the moles as molarity. And the one thing I want you to notice is that we are starting with the product here. So we have NO and Cl starting with. Now, I also want to point out that it's important to take a look at your Cl and pay attention. Your Kc's, I said Cl, I meant your K value, your equilibrium constant. Notice here that the Kc value here is very, very, very small. Well, what does that mean in terms of which side is favored? Well, if the ratio is products over reactants and you have a very small value for Kc, that means that the reactants are very, very much favored. So if you start with only products here, then it's going to go very strongly in this direction. So let's set up our table a little bit. So if we set up our table, right, let's start up the initial concentrations. So we're starting with 1.00 molar here. We're starting with 0.50 molar here, and we're starting with 0 amount here. So obviously it's going to go into this direction because we don't have any reactant here. But because this is small, very, very small, then this reaction is going to favor the reactant here, NOCl. So NOCl, because it's going to be favored very much, it's going to strongly go in this direction, and then we can't assume that X is small. So because it's going to go in this direction such that we're going to have a lot of product, and we'll probably have a little tiny amount of your, we're going to make reactant here. We're going to make a lot of reactant, and we're going to end up with a small amount of product here, right, in the end. But let's go ahead and do this. So what does that tell us? That indicates that we have to do a stoichiometry problem first before we can do any equilibrium problem. So we can assume, for the sake of this particular problem, for part B, we can assume that, let's say, okay, it's going to go 100% in this direction. It's going to go to completion in this way. And then once we do that, we can figure out what the equilibrium is going to be. So we got to do a stoichiometry problem first and have it go to completion, and then we can look at the equilibrium. Okay, so let's go ahead and do that. So we're going to do an ICF table or an IF table. Some people do IF. I like ICF. So here I got the initial amounts. And remember, for your stoichiometry table, you're going to want to use moles, not molarity. But the molarity and the moles are the same, so it doesn't matter. The numbers are the same, but typically, if they're not the same, you want to convert your molarities to moles when you're doing your stoichiometry table. But they gave us moles anyway, and the moles and the molarity have the same numbers because the volume is 1.0 liters, so it kind of works out simply. Okay, so what we want to do is we're going to do the change. So we're going to go 100% in this direction. So we got to figure out what the limiting reagent is, which one's going to run out first, and that's going to go to 0. But if you look here, you'll notice that there's a 2-to-1 ratio here, and you'll notice there's a 2-to-1 ratio here. What that tells us is both of these are going to go to completion, meaning they're going to both run out. So we don't have a limiting reagent, or in a way, they're both limiting in the same way, right? So here, we're going to lose 0.5 moles here because we're assuming 100% reaction this way. Well, if this is 1.05 moles, then we need double the amount here, so that's going to be 1.00 moles here. We're going to lose 1.00 moles here, right? Because it's a 2-to-1 ratio, so this is a 2-to-1 ratio. So we're going to gain here, since we are losing 0.5 moles here, and this is 2-to-1, so that means we're also going to gain a 1 mole amount there. So then we end up with a 0 amount here for the final amounts after the reaction goes to completion, and we're going to end up with 1.00 moles here. And so now we're done with the stoichiometry part of the problem. We've assumed that this is going to go 100% in this direction because it's according to the equilibrium constant, it is going to highly favor reactants over products. So we did the stoichiometry first. We got our final amount after the stoichiometry part. And so now we're ready to start with these amounts to do the equilibrium. However, if you remember from part A, we started with 1.0 moles of NOCl in a 1 liter container. And so after the reaction here in part B, we end up with 1.00 moles and 0 of the amounts here. So we've got the exact same situation we had in part A. So we're going to get the same results in part A, so we don't need to do those calculations again. So concentrations are going to be the same in part A. So I'll write same equilibrium concentrations as part A. And again, the reason for that is because after we did the stoichiometry, we ended up with the exact same starting materials or starting moles that we had in part A up here. So it's going to end up being the same concentrations at equilibrium. Okay, now what about part C? Let's go ahead and do part C. Okay, so let's start over here. Okay, so for part C, we're given 1.00 moles of NO and this time 0.75 moles of Cl2 to begin with in a 1.0 liter container. So again, just like part B, we're going to have to do the stoichiometry first, but this time we don't have the stoichiometric ratio of the moles to start with of the product. So this, we're going to end up with some product left over. So because we're starting with product, it's going to go 100% in this direction. So we have to do the stoichiometry part again because it's going to go strongly in this direction. So X, we can't assume that X is going to be negligible. It's most likely not negligible. So we have to do our ICF table first. Let's do the stoichiometry first. So we'll do the ICF part. So again, you want to start with moles. So we got 1.00 moles of NO, so that's the same as before. So 1.00 moles. And we have 0.75 moles of Cl2, so that's going to be 0.75 moles. And so here, we got to figure out which one is the limiting reagent here, which one's going to run out and go to 0, because we're going to assume completion in this direction here. We're starting out with a 0 amount here. So since this is a 1-to-2 ratio, I am starting with 0.75 moles. In order to react completely with the 0.75 moles of the Cl2, I'm going to need double the amount of NO. So if I double 0.75, I get 1.75. So if I double this, right, I get 1.50 moles. So this is the number of moles of NO that I need to completely react with Cl2. But I don't have enough NO to react completely with this amount of Cl2. So therefore, this is going to run out before all of this reacts. So the NO is going to be my limiting reagent. So that's going to run out first. So I'm going to end up with a 0 amount of this. So I'm going to lose all of my NO. So I'm going to lose 1.00 moles of NO, right? So that means, since this is 2-to-1, if I'm going to lose half of this amount of Cl2. So because 1 is half of 2, so if I start with 1, if I lose 1, then I'm going to lose half of that amount of Cl2. So I'm going to lose 0.50 moles of Cl2. And by the same reasoning, since it's 2-to-2, it's a 1-to-1 ratio. So if I lose 1 mole here, I'm going to gain 1 mole here. So then I end up with, after the stoichiometry, I end up with 1.00 moles, right, of the NOCl. and then I'm going to end up with 0 amount of NO. And then if I subtract 0.50 moles from 0.75, I get 0.25 moles of Cl2 left. So now this is my equilibrium, I'm sorry, not my equilibrium, this is my starting concentrations for equilibrium. So now I can do the equilibrium problem now that I have these here after doing the stoichiometry, assuming that it's going to go to completion in this direction. So now I can reset this up and do an ice table. So let's set up the ice table. So I'm going to put the initial concentrations up here. So now I'm starting with 1.00. Now I'm going to do molarity. I mean, remember, when you're doing equilibrium problems, it's got to be in molarity. When you're doing stoichiometry problems, it's got to be in moles. But because we're working in 1.0 liter container, they're going to be the same. Moles is going to be the same as concentration in terms of the magnitude, the number, right? So 1.00 moles becomes 1.00 molar. This is 0, and this comes up to 0.25 molar. Now I can erase this and start my ice table. Okay, so now that I have 0 here, that means it's going to shift in this direction to reach equilibrium. So now I'm going to write that change going this way. So I'm going to lose a 2x amount there. I'm going to gain a 2x amount here, and I'm going to gain an x amount there. Now I just add them together to get the equilibrium expression. So I get 1.00 minus 2x. This is going to be 2x, and this is going to be 0.25 plus x. And so now I have my equilibrium expressions, or my equilibrium concentrations, in terms of x. So let's go ahead and plug those into my equilibrium constant expression here. So I have NO 2x again. So here we're going to have, again, the Kc value. The equilibrium constant is 1.6 times 10 to the negative 5. That's going to be equal to the NO concentration squared, and the NO concentration is 1.00 minus 2x. Oh, I'm sorry. The NO concentration is 2x, so I'm going to put 2x there, and then it's squared because I have squared up there. Now I'm going to multiply it by the Cl2 concentration, and the Cl2 concentration is 0.25 minus or plus x. So I'm going to put that there. So 0.25 plus x. Okay. So then I'm going to divide that by the concentration of NoCl2Cl squared, and the concentration is 1.00 minus 2x. So here we're going to have 1.00 minus 2x, and that is squared. So again, just as like we did in part A, because the equilibrium constant is so small compared to the starting concentrations, right, 1.00 and 0.25, that we can assume that x is going to be negligible, right? The change is going to be so small that the equilibrium concentration is going to be the same as the starting concentration, the initial concentration. So what that means is we can go ahead and get rid of the x here. So subtracting a 2x amount is going to be so small as to be negligible. And then subtracting an x amount here, or adding an x amount here, is going to be so small as to be negligible. So we can get rid of those. And now we can simplify. So this is going to be 2x squared, which is going to be 4x squared multiplied by 0.25 divided by, and so we have 1.00 squared here. And again, that's going to be equal to 1.6 times 10 to the negative 5. Okay, so now we can simplify more. That's 1, right? So then we got 1.6 times 10 to the negative 5. That's equal to 4x squared times 0.25. We can then divide by 0.25 on both sides, 0.25. So that cancels out, and then at this point we get, what do we get? Oh, I forgot. I forgot. Here, let me back up. This actually simplifies a little bit better. So 0.25. If you recognize 0.25, that's the same as 1/4. We have a 4 here. So 4 times 1/4 is 1. So the 4 here cancels out with the 0.25. So we actually don't need to divide. If you did divide and then divide by the 4, you know, the calculator is going to do the math for you. So it should work out the same. But if you notice that this is a 4 and this is 1/4, then that's just going to cancel out. And then you get 1.6 times 10 to the negative 5 is equal to x squared. And then all you have to do is take the square roots, and then you get 0.004. So you get 0.004 is equal to x. So now we can plug x back into our equilibrium our equilibrium expressions for these different species here. But again, remember, we assumed that x is going to be so small as to be negligible, such that the initial concentration we started with is going to be pretty much equal to the equilibrium concentration. So basically, in that case, since we said that this is so small as to be negligible, that means that the equilibrium concentration of NaCl should be equal to 1.00 molar, and the same thing for these two. So now for this one here, we're going to say, well, since adding x was so small as to be negligible, then the concentration we started with for Cl2 should be the same as the concentration that we're ending with. So that means that the assumption is that the concentration of Cl2 is also equal to 0.25 molar, since the assumption is that the x is so small that our initial concentration is going to be the same as our equilibrium concentration. And then finally, because we have 2x here, the concentration of NO is going to be equal to 2x, which is equal to 2 times 0.004, which means that the concentration of NO is going to be 0.008 molar. So these are the equilibrium concentrations of the species under the conditions of C to start with. And I hope that's helpful. I hope you enjoyed the video. I hope that you learned a lot from this video. If you did, then by all means, like the video, share the video, hit that like button. Also, subscribe to my channel, hit that notification bell up there. When you do that, click all so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me, and have a great day.